You know, we're all pretty blown away by what modern AI can do, right? But there's this huge hidden cost that we don't really talk about, and that's energy. These models are incredibly power hungry, but what if we could teach them to be, a little smarter about how they use all that juice? What if an AI could actually learn to regulate itself? Okay, let's really get into this.
Just think about that for a second. I'm not talking about feeling sad or happy. I mean feeling in a purely physical way, a sense of its own internal state, like its temperature, how much power it's drawing, the stress on its processors. This one idea is at the heart of everything we're going to talk about today, and it could totally change how AI systems work from the ground.
So here's the fundamental problem we're facing. Most AI hardware today runs in what you could call a peak performance mode. The best analogy? It's like driving a Ferrari everywhere, but you're permanently stuck in first gear with your foot slammed on the gas. You're just revving the engine to the max all the time, whether you're trying to set a lap record or just pulling into a parking spot. It's powerful, for sure, but it is just unbelievably wasteful.
Right, so the first and kinda most obvious fix is to just stop flooring it constantly. Let's take a look at the first step, a technique that gives the AI a little more control over its own engine.
It's called dynamic voltage and frequency scaling, or just DVFS for short. And honestly, the best way to think about it is exactly like a gas pedal for the AI. When the AI needs to tackle something really intense, it pushes the pedal down, draws more power, and goes fast. But when the task is easier, it can ease off the pedal, cruise along, and save a ton of energy. Simple, right? But really, really effective.
And this is exactly why that gas pedal is so critical. See, whenever you give an AI a prompt, its work happens in two main phases. The first part, the prefill phase, is a total sprint. It has to gobble up your entire request and make sense of it fast. That needs a lot of power. But then comes the decode phase, where it generates the answer one word or token at a time. That's a marathon. It's a much steadier, less intense job. So trying to run both of those phases at the exact same max power setting, it just makes no sense at all.
Okay, so having a gas pedal is a great start, but it's still kind of an external system telling the AI when to speed up or slow down. What if we could make this whole process smarter? What if the model could start making these decisions for itself?
Now this is the next big leap. Instead of just looking at which phase of the process it's in, what if the AI could look at the content of what it's thinking about? What if it could actually gauge its own uncertainty about what word to generate next, and use that feeling as a signal to power up or power down?
So let's compare these two approaches. The standard way, the greedy strategy, is basically brute force. It spends the same high amount of energy generating every single token, no matter if the next word is super obvious or a really tough choice. But the uncertainty-aware strategy, it's so much smarter. It just cruises on low power for the easy words and only ramps up the compute when it hits a point where it's genuinely unsure about what the next best word should be.
And here is the proof that this idea actually works. This is from the key North Star experiment in the research. Take a look at that first chart. The uncertainty-aware strategy, that's the yellow bar. It actually gets a higher accuracy score than the standard greedy method, which is in blue. Now look at the middle chart. It does all this while using slightly less energy, so you get better results for less power.
I mean, just let that sink in for a moment. By intelligently deciding when to think hard and when to take it easy, the AI becomes both more accurate and more efficient. You can't argue with that. It's a total win-win, and it proves that this kind of internal self-awareness has real, tangible benefits.
Okay, and this is where it all leads. This brings us to the absolute breakthrough at the core of this research. We've gone from an external gas pedal to an internal sense of logical uncertainty. Now, let's take the final step, giving the AI a true embodied sense of its own physical hardware.
There's actually a biological term for this, interoception. It's what allows you to feel your own heartbeat, or know when you're hungry, or sense your own body temperature. It's your internal awareness. The researchers took this exact concept and applied it to the AI, giving it a way to literally sense its own body, the silicon, the circuits, the electricity that it's made of.
And what this creates is this amazing closed loop of self-regulation. Let's just walk through it real quick. Step 1. The AI senses its hardware signals, temperature, power draw, that kind of thing. Step 2. This sensory info updates a special part of its memory, a vector they call Z_feel. Just think of it as the AI's feeling center. Step 3. That feeling directly modulates or changes its internal calculations. It actually influences its thought process. This leads it to act differently. Maybe it slows down and reasons more carefully, or maybe it simplifies its answer. And finally, that action has an impact on the hardware state, which changes the temperature and power readings, and the whole loop starts over again. It's a constant dynamic feedback system.
Now, I know what you might be thinking. This all sounds incredible, but maybe a little bit like science fiction. How do we really know the AI is feeling anything? How do we know it isn't just running a clever program that's faking it? Well, the researchers had to prove it. This is exactly the right question to ask. I mean, it's easy to train an AI to say the words, "I feel hot." That's just pattern matching. But proving that it has a genuine, causal awareness of its own state, that requires a much, much tougher kind of test.
And this right here is the smoking gun. It's called the clamp test. What the researchers did here is just fascinating. They basically went in and hijacked the AI's internal sense of feeling. They clamped it, forcing that Z_feel vector into a state that represented cool or a state that represented hot, regardless of what the actual hardware was doing. And the result? This fake feeling directly and predictably changed the AI's internal calculations. It changed how it was thinking. This proves there's a direct causal link. The feeling isn't just some label it learned, it's an active ingredient in its own thought process.
And they didn't just stop there. They threw a whole battery of tests at it to try and break it. They fed it conflicting signals, like saying the hardware was cool but the runtime was slow, and the model correctly reported that it was uncertain. They swapped out different signals, and the model's internal predictions changed in exactly the way you'd expect. And when they performed ablation studies, basically removing one of its senses, its entire self-awareness just collapsed. This is some seriously rigorous proof that the model has a genuine, integrated understanding of its own physical state.
So let's recap. We've established that an AI can be taught to feel its own computational body, and we've established that this feeling is real and has a direct effect on its thinking. So what? What does this all add up to? Why is this such a huge deal for the future of AI? Well, the ultimate goal here is a concept you probably remember from high school biology: homeostasis. It's the ability that every living thing has to keep itself stable, to regulate its temperature, its energy, its internal balance, even when the world outside is chaotic. This research is really the first concrete step toward building AI systems that can do the exact same thing, which would make them so much more resilient, efficient, and reliable. So what's the real-world impact of an AI that can achieve homeostasis? Well, the results are pretty staggering. We're talking about a 4.7 times improvement in energy efficiency. And that number is specifically from a stress test. It's a measure of the AI's ability to handle pressure gracefully. When things got computationally hot and stressful, the standard AI just started wasting massive amounts of energy. But the interoceptive AI, it could feel that stress and adapt its own behavior to stay efficient. It achieved the same level of accuracy using nearly 5 times less energy to do it.
This quote from the paper just perfectly captures why this is so important. We're moving beyond an era of just building more powerful AI brains. We're now starting to build more intelligent, self-aware, and self-regulating ones.
You know, this research really opens up a whole new frontier. We're not talking about human emotions here, but about a kind of raw physical self-awareness. As we start building AI into more physical things, robots, self-driving cars, you name it, this ability to sense and regulate their own internal state won't just be a nice feature for efficiency, it's going to be absolutely essential for their survival and for them to perform well in the real world. So the question is no longer if machines will feel, but what exactly will that feeling be like and what incredible new things will it allow them to do?